Dr. Rekha?
Am I audible?
Yes, ma'am.
Respected Chief Guest and Resource Person of the Day, Dr. Alexander Kunz, Principal Reverend Father Jolie Andrew CMI, Head of the Department of Geology and Environmental Science, Dr. Lindo Alapat, Coordinator BHOOMITHRASENA Club and Coordinator of this international webinar, Dr. Manju, Deans of Faculty of Arts and Science, IQAC Coordinator, Controller of Examinations, Public Relation Officer, faculty members, students, and participants from various institutions, good afternoon to all. This international webinar is organized by BHOOMITHRASENA Club and Department of Geology and Environmental Science in connection with Decade on Ecosystem Restoration and International Plastic Free Bag Day 2021. Today, we are very much fortunate to have two eminent resource persons, Dr. Kakuli Banerjee, Assistant Professor and Founding Head, Department of Biodiversity and Conservation of Natural Resources, Central University of Odisha, to handle the forenoon session. Now, we have Dr. Alexander Kunz to handle the afternoon session on microplastic pollution of the environment. He is going to focus on two case studies from Taiwan. He works as Principal Investigator and Project Director for Microplastic Research under a special research grant from Ministry of Science and Technology, Taiwan. He took his PhD in Natural Sciences from Leuphana University, Lernberg and Leibniz Institute of Applied Geophysics, Hanover, Germany, and his thesis was on coastal and dune evolution in Southeast India, revealed by optically stimulated luminescence dating, reconstruction of sediment dynamic event history, climatic and environmental change for the last 3,500 years. He also worked as head of the luminescence dating laboratory, and since 2015, he engaged in research about microplastic in the environment. With immense pleasure and gratitude, I would like to extend a warm welcome to our resource person to this program. And also, it is my pleasure to invite Dr. Alexander Kunz to handle the session. I hope you have an enriching and wonderful session ahead. Thank you.
Thank you, ma'am. I proudly welcome Sir for taking up the session.
Over to you, Alex. You may start now.
Okay, so can I start? Yeah, thank you for the introduction and also the invitation to give me the opportunity to give a presentation about microplastic research here in this seminar. I'm trying now to start a presentation. Can you see the slides?
Yes, Alex.
Okay. Okay, good. Yeah, so today I'm talking about the microplastic pollution of the environment, and I will present two case studies from Taiwan, which we did in the last couple of years. And my presentation will be consisting of two parts. The first part is a general introduction. So what is microplastic? A little bit about the history of microplastic research. What are the major sources of microplastic? Then I will talk about the global amount of microplastic and also the problems of microplastic pollution. And in the second part of my talk, I will present then the study in Taiwan. One study is about microplastic pollution in beaches. And the second one is about the pollution of the Danshui River and its main tributaries. So basically microplastic in freshwater environments. So I'm coming to the first part. So microplastic is any kind of synthetic polymer or plastic that is smaller than 5 millimeter in size or smaller than 1 millimeter in size. So there are two size definitions, and I will talk about that a little bit later. And you might hear the words microplastic and microplastics, and this is actually the same. So it's no difference in between both. And the images here, they show you a few examples of microplastic pieces. They are a little bit larger, but they can be much, much smaller. And microplastic was first described as a part of marine litter. So marine litter is generally subdivided in different groups according to the material, which can be cloth, glass, and ceramic. Then there's a group of plastic, metal, paper, wood, and so on. And within that plastic group, it's further subdivided according to their size. And everything larger than 25 millimeters in size, it's macroplastic. Everything between 5 and 25 millimeters is called mesoplastic. Everything between 1 and 5 millimeters, it's called large microplastic. And everything smaller than 1 millimeter is called microplastic, how you know it. And then there's also rarely used a subgroup, which is everything smaller than 0.01 millimeters, and that's called nanoplastic. This is rarely used. Also, the word nanoplastic is a bit confusing because it can be mixed up with nanomaterials. And interesting to know is that the size definition was arbitrary. So there's actually no real reason why it is like that. And it originated mainly from observations during beach cleanings, because the size 25 millimeter is the size of a bottle cap. So everything what is larger than a bottle cap was defined as macroplastic. And plastic debris in general is, as I mentioned, there's macroplastic and microplastic. And normally the large pieces are subdivided according to the item, what it is. So like bottles, food containers, plastic bags, and so on. And the smaller items are subdivided according to their form or their type, because you cannot tell what it was originally. So when we talk about microplastic, we will see fragments, pellets, foam, and other items. Later, I will show you a few pictures of this. Here are a few examples of macroplastic. I think everybody who went to a beach knows these things. So on the left side, you can see these are containers from aquaculture. They're, I think, used for bait. Then, of course, plastic bottles, plenty of plastic bottles you can find on beaches, and these floaters from fishing nets. And you can also see already smaller pieces scattered around, like this one here, or this one, what I'm circling now. These are actually microplastic pieces. And these are the common microplastic types. So these are film. These are very thin and flexible pieces. They are mostly originating from plastic bags or these kind of plastic packing material. Then there's a large group of fragments. This is any kind of plastic piece that broke away from a larger piece. And there's also a big group of so-called foamed plastic, which is mostly styrofoam, but there are also other foamed plastic types. Then there are pellets. Pellets are quite interesting because these are the raw materials from the plastic industry. So when plastic is produced, it is produced in the shape of these kind of cylindrical pellets, and then they are transferred to the actual plastic manufacturing where they are molten and then formed into the object. And the egg-shaped ones, these are the weathered pellets. And then, of course, fibers. So the whole fibers are actually a huge amount of fibers you can find. Yeah, I would now talk a little bit about the history of microplastic, because in the last few years, microplastic has become a very popular topic in mainstream media and popular science. But if you look, this is a search from Google Trends, how often something about the topic of microplastic was searched. And this is from 2004 going up to today. And you can see that only in the recent years, starting somewhere around maybe 2016, 17, the interest rised a lot, peaked in September 2019, and then it dropped sharply. And yeah, what happened in September 2019, why there was suddenly so much interest in the topic? That was the time of all these environmental movements like Fridays for Future. There was suddenly a big interest in marine pollution and microplastic pollution, all sorts of environmental pollution. But it dropped sharply because then this guy appeared and changed everything. So now we have another focus. But also in science, you can see a similar pattern. So that science actually, or research actually started only a couple of years ago to focus on microplastic. These are the number of publications for the marine environment and the dark gray for freshwater. And the beginning, it really started around 2011 probably. And then there's a big rise in research in the topic. And freshwater is now increasing as well. But microplastic, even though we are now focusing a lot on this topic, has been in the environment since a long time. One of the very first studies was in 1972. And this was one of the first observations of microplastic pieces in the ocean. And these were these industrial pellets, which I just showed you before. And in this study, they found about 3,500 pieces per square kilometer. This is already quite significant amount. And that's actually quite interesting if you look at the history of plastic production. So in the 1950s, the plastic production started, the mass production. And you can see in this chart on the right side that the amount of plastic that is produced is growing at a very fast rate. But already like 18 years later, first reports about plastic in sea turtle appeared, and only 20 years after the production of plastic, the first occurrence of microplastics was documented. So that means it took only 20 years to pollute the oceans. And only since about 2005 we are, and it was estimated that about less than 1 up to 250 microplastic particles can be generated by cutting 1 centimeter of packing material. Another main source of microplastic is road traffic, so tire abrasion, and it was estimated that in the US, every year 1.1 billion tons of particles are released only from tires. In the European Union, it was estimated these are 1.3 million tons per year, but the global amount is very likely much, much higher. Then industry is the third largest source for microplastic. So this can be, for example, cutting and grinding of plastic material, disintegration of styrofoam. This is a very, very big issue, especially with the fishing industry, since everything is packed in styrofoam boxes and then they break and the stuff goes into the ocean. And the spill of pellets. So industrial pellets, when they're transported, this transport is quite careless, and it's not uncommon that these boxes or these containers, they break and material is spilled out. And in a study in, I think it was in Sweden, they found that around one production site between 3 up to 36 million pellets every year are released into the environment just simply from careless handling. And the last major source for microplastic is simply degradation of large plastic items. So when plastic is in the environment, it's exposed to UV light, to heat, to cold, to the seawater and other agents, and it will degrade after a while. So large pieces will break and produce smaller pieces. They will break, produce even smaller pieces. And in general, it's about 350 million tons of plastic waste are produced in 2014. Most of it goes to the landfill, 200 million tons. Smaller amounts are incinerated or recycled, but from all this plastic, up to 12.7 million tons are released into the oceans. This is every year happening. So that means that every year we have we are increasing the amount of macroplastic in the oceans, which is then basically an endless reservoir for microplastic generation. And it is estimated that the global amounts of plastic or microplastic that's floating in the ocean, so very early estimate was that these are 250,000 tons of plastic floating in the world's ocean, but this is probably way underestimated, because recently it was found that only in the top 200 meters of the Atlantic Ocean, already up to 20 million tons of plastic are floating. Rivers discharge every year up to 2.4 million tons of plastic into the oceans. And in the deep sea sediments, it is estimated that there are already 40 million tons of plastic deposited. But these numbers are all based on research that is done on relatively small scales. So these numbers are probably still underestimating the true amount of plastic in the environment. So why is microplastic problematic? On one side, it can cause injury or death because animals are ingesting it. So it can damage the digestive or the intestines. And the second problem is that plastic can release and uptake pollutants. And once these pollutants can either just be released into the water, or animals eat the plastic and then the pollutants go into the animals and enter the food chain. And microplastic ingestion is actually a big issue for animals because they cannot distinguish the plastic particles from natural particles or natural food. And a lot of plastic, when it's floating on the sea, there's a biofouling happening, so that algae starts to grow on this and other animals start to grow. So basically the plastic itself is covered by something eatable, and animals would just simply swallow it, and so they're ingesting the plastic particles. And in the worst case, they can accumulate in the digestive tract without being released, so the animals more or less starve to death. And many studies have already shown that microplastic contain quite a lot of pollutants. And these pollutants can be these like DDT, for example, which has been forbidden since the 1970s, but it's still in the environment, so plastic particles will take them up. But there are also recent materials like these phthalates, these softeners that are used to make plastic soft. It's not really clear, but it's they are how to say, suspicious that they are having hormonal effects. But there are also many others, like flame retardants are used in plastic, which have toxic effects or hormonal effects. So for many items, we still don't really know what's actually happening with them. And these pollutants, so when they are staying in the aquatic environment, because they are hydrophobic, they want to actually find something where they can bond and leave the water. And plastic is actually very attractive for them because they can easily bond to plastic. And there are two ways of bonding. They can either be absorbed from the plastic. So when it's plastic with a structure that has some space, then the chemicals will go inside, or they can stick to the surface and be adsorbed to the plastic piece. And when they're on the surface, then we have a next problem, that the breakdown of plastic into smaller pieces creates more surface area for these chemicals. So if you see the cube, for example, which has a volume of 1 cubic centimeter, it has a surface area of 6 square centimeters. But if you break it into smaller cubes, the volume of these cubes is still 1 cubic centimeter, but the surface area is now doubled to 12 square centimeter. And these smaller cubes or smaller pieces are even more likely to be eaten by animals. So that actually gives then the end result that plastic particles and the chemicals that are attached to the plastic particles enter the food chain and migrate through the food chain until they reach the humans. And in the last few years, it has been shown that humans consume quite a significant amount of microplastic. There have been a great variety of food items have been shown that they contain plastic. This is, for example, seafood. Basically, all kinds of seafood contain microplastic particles. Microplastic can also be found in tap water and bottled water. It was found in beer, but that study is a bit questionable about beer. It was found that plastic milk bottles shed plastic particles into the milk. In sugar it was found, and in sea salt. And sea salt, basically every sea salt you can buy today contains microplastic. And then microplastic is floating in the air, so we are also breathing it. And it was found in human stool. So that means that the plastic particles, after we ingest them, passing through our bodies. The amount, so how much everybody is consuming, depends strongly on your lifestyle, region, age, and gender. So for example, if you don't eat a lot of seafood, then the risk of eating a lot of microplastic is lower. But for people who consume a lot of seafood or a lot of sea salt, they have actually quite high risk of being exposed to microplastic. And currently, the biggest research question in this regard is, of course, what's actually happening with the microplastic particle inside the human bodies, or in general in organisms, how they are interacting with the tissue, if they are releasing chemicals, and what's going on. And that's actually currently unknown. Okay, I will come now to the second part of my talk, where I will introduce the case studies from Taiwan. And I just go quickly through that slide. Is a quick overview about research in Taiwan. I will not mention them in detail, just show you quickly. The main point here is what I want to show is that Taiwan joined the party quite late. Microplastic research more or less started around 2016, 2012. This is the earliest studies. And only now, since 2020, there's actually quite a lot of work done in Taiwan. Okay, now I will talk about the research project I'm working on. This is about microplastic in beaches. And this was a study I did in North Taiwan. We studied 3 beaches during the time from April 2018 to November 2019. And we wanted to know, how is the microplastic distribution affected by typhoons? So we collected samples over different time periods, especially directly after typhoons, and observed how the composition or the appearance and the distribution of the particles on the beach changed. During that study, we collected almost 2,000 kilograms of beach sand, and then extracted more than 12,000 mesoplastic particles and nearly 89,000 microplastic particles. We did not study this one. We started here, but this beach we had to stop working there. I will show you just now why. But first of all, during that time of the study, we were quite lucky because there were 3 typhoons, super typhoons passing by close by Taiwan. And this was Typhoon Maria in July 2018, then Typhoon Lekima in August 2019, and Typhoon Mitak in September 2019. None of them made landfall on Taiwan, but they came actually close enough to have strong impact onto the beach. And this is the beach, Dozer one, which I just mentioned, where we had to stop working because the beach erosion was so strong that there was actually nothing to sample for us. The upper picture, you can see that was in May 2018, and 1 year later, there was so much sand eroded during the time that even the rocking on that, but the other 2 beaches, we could continue our study. And this is Shila Beach in Jinshan. This is in North Taiwan. This is a picture showing the beach, the top one in May 2019, and the lower one is in August 2019. This is just after a few days after the Typhoon Lekima passed by. And you can already see quite a big difference in the beach, in the morphology, and also that a lot of material was deposited very high at the end of the beach. And a very interesting effect after typhoons is always that the beaches are cleaner or appear cleaner than they have been before the typhoon. And this is the other beach we studied, that's Longman Beach in Gongleo in the northeast of Taiwan. Again, the upper picture shows the beach in May 2018, and the lower one is in July 2018 after Typhoon Maria. And here you can see the same, that all the material due to the strong wave action has been pushed to the coastal dunes at the end of the backshore. And for the beach study, we used the sampling method that we collected sand from the surface. And we had 3 parallel transects. And we always sampled from a square of 50 by 50 centimeter, which is a standard size for beach samplings. And the transects have been always 1 meter apart, and each sample was again 1 meter apart. And we sampled on random days during non-typhoon seasons to have something like baseline or background pollution level. And then we sampled immediately after the typhoon. And I want to, yeah, you can see on that image, I hope you can see it. There are the transects, they're starting in the dune, and then they're going all the way down to the water line. And perhaps you can see the sampling bags lined up here. And I want to quickly introduce the different beach zones so then you can better understand what I'm talking in the next slides. So at the end of the beach, this is the dune. And then in this case, you have 2 storm lines. So this is the old storm line running here where you have debris accumulated. And this is the recent storm line, again, with a higher amount of debris accumulated. Then the high tide line. This is where during the tides, the wave reach. This is the maximum reach of the wave during a tide. And the areas between the water and the high tide line is called the intertidal. The area between high tide line and recent storm line is the supralittoral. So this is the waves frequently reach, but not constantly. And the area behind the storm line is the backshore area. And these are the microplastic counting results. This is just one example, just to illustrate how the distribution looks like and which effects we can observe. So each of these numbers represents the number of microplastic particles in one of these sample squares. So in the size of 0.25 square meter. And we start here, this is in the dune, and go all the way down to the intertidal. And what you can already hopefully see is that the high tide line at the storm line, or both at the recent storm line and the old storm line, the amount of microplastic is the highest, whereas in other areas like the supralittoral or the backshore area, the number is the lowest. So you can see that the accumulation of microplastic follows actually the wave energy. And you can also see something quite interesting and important actually for microplastic research, that there's a large variability between samples. So if you look, for example, here at the backshore, you can have 1 square with 0 particles. The next one can have 6 particles, and you can have suddenly 33 particles. And they're only 1 meter apart. And the same happens also when you go lateral between the transects. You can have very high numbers, like for example, here in the recent storm line, and 1 meter to the side, you can have suddenly almost no plastic pieces. And this high variability is actually something you really need to consider when you want to study microplastic in the environment. And this is the example how the distribution looks like after typhoon struck. And as you can see, all the material is now pushed by waves to the coastal dunes at the end of the beach. This is again the same beach, the same way of sampling. And all the plastic particles have been accumulated now at the end of the storm line. The part in front of the beach is almost clean. There's really nothing. Everything is moved at the end, and also the amount of microplastic has increased significantly after typhoon. Another quite interesting effect we can observe on that beach is when we look at the different shapes of the plastic particles. We can see that, so the dark color represents the fragments, and formed plastic particles are the light colored, and pellets are the one on top. And normally during normal weather conditions, we have mostly fragments and a small amount of formed plastic particles, but after typhoon, the ratios change dramatically. So there are much more foam particles on the beach and only a few fragments left over. And this we can observe for all 3 typhoons. For microplastic, also for the larger particles, for mesoplastic, we can see the same trend that after typhoon, the amount of foamed plastic significantly increases. At this stage of the research, it's not really clear why there's so much more foamed plastic after the typhoon hit the beach. And this is also a little bit contradictory because foamed plastic is 10 times lighter than fragments. And during typhoons, the wave energy is much higher. So you would actually expect that more heavy material reaches the beach and that all the light materials are removed from the beach. Also, the wind is during typhoon much stronger, so that foamed plastic should be blown away much further to the dunes. But that's actually not the case. And one hypothesis is that maybe there's much more foamed plastic offshore, and during the typhoon, it's all brought to the beach and deposited on the beach, or that when the beach is flooded during typhoon, because the waves are reaching far into the dunes, that there are undercurrents that are removing the heavy particles, and only the light particles which are floating on top of the water are settling down onto the beach. And from the beach study, the preliminary results are the typhoons have a very strong impact onto the microplastic amount, but also the shape assemblage and the deposition patterns. You can also see that there's a very high dynamic on the beach happening, so that even after a few weeks of sampling, so when we return to the beach sample again, the distributions patterns have changed strongly. And the deposition of the plastic particles follows the wave energy, and most of the microplastic gets deposited at the storm line and not at the high tide line. Previous research always indicated that high tide line is the one with the highest amount of plastic, but our results show that actually it's the storm line. And we think that microplastic or plastic in general actually is a good indicator, or could be a good indicator for wind or wave energy, as the deposition follows usually the wave energy. Okay, now I will come to the last part and just quickly talk about microplastic in freshwater environments. This is a study we did about 2 years ago about the microplastic pollution of the Dozer River in northern Taiwan. And rivers are in general a major contributor of plastic waste into the oceans, but rivers are also quite an important source for fresh water and drinking water. So it's actually very important to keep rivers clean. And the Dozer River Tamsui River was ranked as one of the top 20 most polluting rivers globally. But the study where the river appeared in this ranking used modeling data, not real field data. So one of the aims in the study was actually to collect real field data about the plastic pollution of this river. And we sampled the main river. So this is the main river, Dozer River, and its 3 tributaries, the Dahan River, Xinjiang River, and the Geelong River here. And we sampled every 2 weeks over a period of 3 months from different locations on the river. And we wanted to get an estimate of the amount of microplastic, also to see temporal trends, and also to get a mass balance. During that time, we filtered about 680,000 liters of river water and collected in total 16 or more than 16,000 microplastic particles in the size range of 0.3 to 5 millimeters size. And for sampling in river, we used a modified Manta net. This is a bit smaller than the one you know from marine research. And we either dropped it from bridges. So we used bridges that are very close to the river mouth that are also accessible. And we had different locations on the bridges to cover the most of the flow. path of the river. And we also try to use a boat for sampling. And yeah, these are the numbers. There's a large variation in numbers. So the amount of plastic particles can range from very low, like 2.8 pieces per cubic meter of water, but can go up to 83 pieces per cubic meter of river water. We can also see that the uncertainties are very high. I will explain that in the next slide why this is the case. So the samples or the results show that there's a large variation within the river, but there's not a large variation within the replicates. So every time we sampled from one location, we took 3 or up to 5 replicate samples. And when we look at the amount of pieces or microplastic pieces from each of the replicates, they are very, very close together. As you can see in the upper part, they're all around 20 pieces per cubic meter. Here something like 11, and here around 6 to 7 pieces per cubic meter. But of course, when you start averaging everything, and especially over the entire river, you're introducing a huge variation. That's why the results have these large variation. It doesn't mean the data is bad, it's just simply from the averaging. And we could also see that the microplastic amount in the rivers correlates with precipitation. Especially, it was very clear for the Xinjiang River, one of these rivers. There was, at the time when there was strong rainfall, the amount of plastic particles increased strongly. But there's also, it looks like that there is a certain threshold value the precipitation needs to reach until more plastic is in the river. And this could be because plastic can be deposited at the river banks, and only when the river water is high enough or strong enough, it can reactivate these plastic particles, so that only after a certain amount of precipitation you will get higher levels of microplastic pollution inside the river. Another important effect or thing to consider when sampling from rivers is that the correlations or the sample results and everything depends strongly on the position where you sample from the river. As I showed before on the slide, there are differences depending if you are in which position of the river you are. This is mostly because of obstacles inside the river, or that the flow path is different, so you can have different microplastic concentrations. One thing that was in, it's a little bit, what to say, difficult to explain. What is the origin of microplastic? Normally, it's assumed that microplastic breaks down from large pieces, but the rivers in Taiwan are very, very short. The longest one, the Dahan River, so this one here, is just 135 kilometers long. And the travel time of the water from the source to the river mouth here can take only 2 to 28 days, depending which river it is. And this is way too short for plastic to disintegrate. So that's why we think that the microplastic we find in these rivers here is produced already on land. And there's a lot of evidence for that, especially in big cities like in Taipei. There's a dense network of storm sewers. And this is a map on the right side that shows the storm sewer network for Taipei city. And these storm sewers they drain directly into the river, so there's no water treatment in between them. And when there is, like in this photo on the left side, some plastic rubbish lying next to the gutter, it will be flushed into it and then goes into the storm sewer, and from there straight into the river. But there are also many households that are connected to a storm sewer, so that the water drainage just goes into a storm sewer, not to the water treatment plant. Another possible source could also be that the plastic we find in the rivers is from the ocean, because the Tamsui River network is affected by semiurnal tides, and the tides, they reach up to 35 kilometers into the river system, and they're pushing all the water from the ocean into the river. So there's a high probability that also plastic from the ocean will enter the river system. And and the residence time of the water is 1 and 2 days. So there's actually enough time for particles to travel upstream. And indeed, we found weathered industrial pellets in the river samples, which you normally only find in the ocean or on beaches, and you should not find heavily weathered particles in the river. So that's why we think that that the ocean might be a source for the particles. But this is something that we need to study further. And in the future, we want to focus the research on the spatial distribution, not only from different points on the river, but really like transects over the river, but also on deeper parts, because we still don't know how much plastic is actually carried in the water column of the rivers. We still need to identify the land-based sources where the plastic actually enters the river, but also study the tidal input, how much of material is brought back from the ocean into the river. And then we can actually give a realistic estimate of microplastic in the Tamsui River system. Yeah, so I'm coming now, this is the last slide, and I want to quickly summarize my talk from today. So what have we learned about microplastic in the environment? So the first thing is microplastic is ubiquitous. It occurs in all environments. It has been found everywhere, from the oceans to the deep sea, to the Arctic, to cities, to places where no human was before. Plastic is everywhere. It occurs also in living organisms and food. The second thing is that microplastic is heterogeneous. So that means that neighboring samples can have large variation in particle numbers. And that's actually something very important when somebody wants to study microplastic in the environment. You need to consider to take a lot of samples to get a good overview of the spatial distribution. There's also a large variability of microplastic, a large spatial and temporal variation in the amount of particles. As you could see in the beach samples, depending what kind, if there's a storm event or not, you can have suddenly 10 times more particles than during a non-storm event. And yeah, microplastic numbers, what we see are kind of inaccurate at the moment, because most studies are only giving snapshots in time and space. So if you would repeat a study and sample at a different time or at a different location, you will get very different results. And that's also something you need to keep in mind when you see results, that they only represent the numbers that have been collected at that time, at that space. And it's really hard to extrapolate microplastic results to the future. Okay, yeah, that's all. If you want to stay updated about the research we are doing, I'm running a Facebook page and a website, which is sometimes updated at the moment, not so much, but yeah, if you want, you can join these things. And I'm finishing now. I don't know if people can ask questions now or.
Yes, Alex, if interested, they can ask questions if they have any questions. Yeah. Hello, I request the moderator to take up some questions, if any questions from the students or participants.
Okay, I see one from the chat. Okay, I see some. Okay, I can read some questions from this chat. So what are some possible solutions for the issues caused by microplastics? Yeah, that's quite difficult to answer, because we don't really know the issues that are caused. The easiest way is to avoid simply releasing plastic into the environment and the further accumulation of microplastic. It's very difficult to remove microplastic from the environment. Once it's there, it will stay there more or less forever now. The next question I see is, does microplastics will persist in human body if it enter into the body? Yeah, this is better to ask a physician, not really a geologist. What I know is there are studies that show that microplastic comes out of the body when you go to the toilet. But maybe something remains in the body. I don't know. There are animal tests with clams or mussels, and they found that microplastic particles, when they're small enough, can go into muscle tissue. I don't know anything about this kind of research for human bodies. So another question I see, does microplastic affect coral reefs? Yes, it does. There has been research done, and they found that corals incorporate microplastic into the reef. So when they build their structure, there you can incorporate microplastic, and that is because it's softer, it's not as stable as the calcified stuff they have. It can affect the stability of a reef. Next question, microplastics accelerate growth of disease-causing microbes. Yeah, this I cannot answer because that's not really my field. People think that microplastic can act as a vector for microbes or viruses because things get attached to the surface, but I cannot say if this, how the effects are, what it actually does.
Yeah, any other questions? If any participants have any other questions, you may ask in the chat box or unmute your mic and ask.
Okay,
Yes.
see. Does microplastic cause biomagnification? I don't know. Sorry for these biological questions. It's not really my field, so I'm not really the right person to answer this. Sorry. Okay, next question I see, how can we control microplastic pollution? Yeah, this is actually a very, very good question. The best way is, as I said, don't release plastic into the environment. What's now in the environment, it's there, we can't do much about this. But if you want to reduce microplastic, you should try, for example, when you wash clothes, maybe insert a filter to catch the fibers, or when you deal with items that shed plastic, where you know, don't wash them into the sink, don't wash them with water, try to collect it and put it into the garbage. Most of the garbage gets burnt, so the plastic will be burnt and removed. I think that's the easiest way. Currently, there are research done how to get rid of microplastic from water treatment plants. But this is still something that's not used on large scale. So at the moment, there's no way of removing microplastic from the environment. Yeah, another question I see, what is the difference between primary and secondary microplastics? So primary microplastic is the one that is produced as a small particle. For example, like these industrial pellets, they're already produced as a small particle, or microbeads that are used in cosmetics. These are primary. And secondary microplastics is any kind of particle that comes from a larger one. So when a plastic bottle breaks into smaller pieces, these are then secondary microplastics. Next question, what can we do about microplastics present in air? Yeah, I don't know, actually. I mean, it's floating in the air. The only thing is everybody by itself can do is using filters to filter it out for the breathing air. But the question is also how much microplastic is floating in the air and how strongly it affects our health. So this is something that has not been researched yet. So we actually don't know what's the effect. Next question, what does shape of microplastics could give information of? Sometimes we can tell from the shape what item it was or where it comes from. So for example, like industrial pellets, that's very clear that it comes from industrial production sites. Sometimes we can relate styrofoam, for example, to fishing industry. It has been found that near fishing harbors, there's always a lot of styrofoam. Fibers are usually coming from washing clothes. But in most cases, the shapes are so unspecific that it's really hard to tell where it comes from or what it was originally. Or any other questions?
If there are no other questions, we may conclude the session. If anyone have the questions, you may unmute your mic and ask to our resource person, or else we will go to the next part of the session.
Okay, I see one more question. It's a question regarding your research paper, microplastic contamination of table salts. Are there any techniques to remove microplastics from already extracted salt? Yes, you could dilute the salt into water, filter everything, and then evaporate the water again to get salt back. But then you won't have natural sea salt anymore, and people probably don't buy it. But there are techniques to do that, yeah. But I think it's probably also too much effort for companies to do that.
Okay, so I see no other questions coming up. Yeah. Then I think we may, yeah, please.
Okay, sir. Thank you, Alexander, sir. That was a very informative section you gave us. As all good things come to an end, I request Dr. Lindo Alapart, Assistant Professor, Head of the Department of Geology and Environmental Science, to thank one and all present here.
Yes, Alex, there was one more question in the chat box. If you want to take it, you may take it.
Yes, how does geographical shape of river affect microplastic shape? Good question. I don't